Every time water disappears down a drain, another hidden journey begins. A shower ends, a toilet flushes, and a sink empties. The water does not simply vanish beneath the floor. It enters one of civilization's most important unseen systems. That system protects streets, rivers, and public health. It carries waste away from millions of people every day. Then it cleans the water before returning it to nature. The process runs continuously through every hour of the night. Pumps lift, screens catch, tanks settle, and microbes consume pollution. Operators monitor flow, oxygen, chemistry, and equipment without pause. Most people never see any of this machinery. Yet without it, a modern city would quickly become unlivable. This is the hidden machine beneath every drain. This is the sewer and wastewater system. The journey begins inside homes, offices, hospitals, and factories. Every plumbing fixture connects to a network of drain pipes. Gravity pulls wastewater downward through vertical stacks. Water traps beneath sinks block dangerous sewer gases. Roof vents allow air to move so drains can flow smoothly. Small interior pipes merge into larger building drains. The building sewer then connects to the public network. From there, gravity usually performs most of the work. Municipal sewers are installed with carefully calculated slopes. Too little slope allows solids to collect and harden. Too much slope lets water rush ahead of heavier waste. The correct slope keeps water and solids moving together. Neighborhood pipes gradually merge into larger interceptors. Those interceptors carry enormous volumes toward the treatment plant. Some cities use separate pipes for sewage and stormwater. Older cities may combine both flows inside the same tunnels. Heavy rain can overwhelm these combined systems within minutes. When capacity is exceeded, polluted overflow may reach rivers. Modern upgrades separate rainfall from household wastewater. Gravity cannot move sewage uphill or across every landscape. Low areas therefore depend on underground lift stations. Wastewater collects inside deep wet wells below the street. Level sensors watch the rising water continuously. Powerful pumps activate before the wet well becomes full. They push wastewater uphill through sealed force mains. Check valves prevent the pressurized flow from reversing. Backup pumps and generators protect the station during failures. From every route, wastewater eventually reaches the treatment plant. The first treatment area is known as the headworks. Large debris must be removed before it damages equipment. Bar screens catch wipes, plastics, rags, and branches. Fine screens remove smaller objects from the incoming flow. Captured debris is washed, compacted, and transported away. The screened water then enters grit removal chambers. Sand, gravel, and broken glass sink faster than organic waste. Removing grit protects pumps from abrasion and blockage. Some plants also remove fats, oils, and grease here. Air bubbles lift floating grease toward the surface. Mechanical scrapers collect the floating layer for disposal. Meters record how much wastewater is entering the plant. Rainstorms can multiply the normal flow several times over. Operators adjust gates, pumps, and tanks to manage the surge. Wastewater next enters large primary settling tanks. The flow slows until gravity can separate heavy material. Dense solids sink and form a layer of sludge. Fats and oils float upward toward the surface. Slow scraper arms move both layers toward collection points. Pumps carry the settled sludge towards separate treatment. The remaining water looks clearer, but is still polluted. Much of that pollution is dissolved or too small to settle. Mechanical separation alone cannot remove it efficiently. The next stage, therefore, uses living microorganisms. These microbes consume organic pollution as food. They need a steady supply of oxygen to remain active. Large blowers force air through diffusers beneath the tanks. The water becomes a moving mixture of air, waste, and biology. This process is commonly called activated sludge treatment. Operators control oxygen, temperature, mixing, and retention time. Too little oxygen weakens the microbial community. Too much oxygen wastes enormous amounts of electricity. The goal is a stable ecosystem inside concrete basins. After aeration, the mixture enters secondary clarifiers. Microbial flock settles toward the bottom of each tank. Clearer water rises and spills over collection weirs. Most settled microbes are returned to the aeration basins. This return flow keeps the biological population strong. Excess sludge is removed to prevent overcrowding. The water now appears much cleaner than before. But appearance alone does not prove that it is safe. Nutrients and microorganisms may still remain in the water. Excess nitrogen can feed destructive algae blooms downstream. Special treatment zones encourage microbes to remove nitrogen. Other processes capture phosphorus biologically or chemically. Sand and cloth filters remove remaining fine particles. Advanced plants may use membranes with microscopic openings. The treated water then reaches the final disinfection stage. Chlorine can destroy many remaining disease-causing organisms. Ultraviolet light disinfects without leaving chemical residue. Some facilities use ozone for additional treatment strength. The chosen method depends on standards and local conditions. Laboratories test bacteria, nutrients, solids, and oxygen demand. Online sensors watch the final water in real time. If quality changes, alarms demand immediate action. Only compliant water is allowed to leave the facility. Treated water may return safely to a river. Coastal plants may send it through long ocean outfalls. Some cities reuse it to irrigate parks and landscapes. Industries can use reclaimed water for cooling and processing. Advanced purification can replenish aquifers and reservoirs. In some regions, recycled water eventually becomes drinking water again. The water cycle has always repeated, both naturally and artificially. The real question is how carefully every barrier is controlled. Cleaning water also creates large quantities of concentrated sludge. Plants first thicken that sludge to reduce its volume. Many facilities then send it into sealed anaerobic digesters. Microorganisms break down the organic material without oxygen. This process produces methane-rich biogas. The gas can fuel boilers or generate electricity on site. Treatment plants cannot solve every problem on their own. Wipes can block pumps because they do not break apart easily. Fats and oils can harden inside sewers and form fatbergs. Industrial chemicals may damage the living treatment process. Cities use pre-treatment rules to control dangerous discharges. Public behavior therefore affects the entire hidden network. Aging pipes create another growing challenge beneath cities. Cracks allow groundwater to leak into sewers during wet weather. Tree roots can enter pipe joints and trap solid waste. Corrosion can weaken large concrete and metal tunnels. Utilities inspect sewers with cameras, sonar, and robots. Trenchless repair can renew pipes without excavating whole streets. Storage tunnels can hold storm surges until plants recover. Green roofs and rain gardens reduce water entering the network. Permeable pavement lets rainfall soak into the ground naturally. Separated sewers reduce the risk of polluted overflow. Resilient cities combine underground engineering with surface design. The future wastewater system will be smarter and more circular. Every drain is an entrance to this hidden world. Every sewer pipe carries the consequences of city life. Every treatment tank protects the water beyond the city. The process begins with waste and ends with recovery. Gravity, pump microbes, chemistry, and human judgment work together. The system is dirty, complex, and absolutely essential. It allows millions of people to share dense cities safely. It protects rivers from the waste that cities produce. An entire hidden machine is waiting beneath every drain. That is how the world works. Every second, modern life depends on a machine you rarely see. You touch a switch, and darkness disappears instantly. Your phone charges while you sleep. Your refrigerator protects food without asking for attention. Traffic lights coordinate thousands of strangers. Elevators rise, trains move, and hospitals keep breathing. SIRS keep messages, money, and information moving. Factories continue working long after sunset. Water pumps push life through buried pipes. Entire skylines remain bright against the night. All of it relies on one invisible system. The power grid is civilization's machine that never sleeps. To understand it, begin where electricity is created. Electricity starts with energy from nature or fuel. In thermal plants, heat turns water into steam. That steam spins a turbine at enormous speed. The turbine drives a generator filled with magnetic fields. Coal and gas plants follow versions of this process. Nuclear plants create heat through atomic fission. Hydroelectric dams use the force of falling water. Wind turbines capture motion directly from moving air. Solar panels convert sunlight directly into electrical current. Different sources feed the same interconnected network. Generation must constantly respond to changing demand. Power must be available almost the moment it is needed. But producing electricity solves only half the problem. The other half is moving it efficiently. Electricity loses energy when current heats the wires. Longer journeys can mean greater energy losses. The grid reduces those losses by raising voltage. Higher voltage moves the same power with lower current. Lower current means less heat wasted along the route. Step-up transformers perform this crucial conversion. Then electricity enters the high-voltage transmission network. Steel towers carry it across enormous distances. Some lines cross mountains and deep valleys. Others cross rivers, forests, and deserts. Power may travel hundreds of miles before reaching users. Grid operators can route energy between entire regions. This network lets distant generators support crowded cities. Without transmission, power sources would remain isolated. With transmission, remote energy becomes local life. Transmission voltage is far too high for ordinary buildings. So electricity must be transformed again near demand centers. Substations are the traffic junctions of the grid. They receive power from major transmission lines. They route electricity toward different districts. They also disconnect damaged equipment during faults. Large transformers reduce voltage to distribution levels. From there, electricity enters local networks. These smaller lines weave through neighborhoods and suburbs. Some run above streets on utility poles. Others remain buried beneath roads and sidewalks. Distribution networks serve homes, schools, and businesses. They also support hospitals, stations, and emergency services. Local transformers reduce the voltage one final time. A gray cylinder on a pole may serve several homes. Electricity then reaches the building's service connection. A meter records how much energy the building uses. Breakers divide and protect the building's circuits. Wiring carries electricity to every outlet and appliance. A continental network can end at one small lamp. The journey is immense, but the result feels effortless. The grid's greatest challenge is maintaining perfect balance. Most grid electricity is produced while people consume it. Supply and demand must match almost every second. Demand changes whenever millions of people change behavior. Morning begins with lights, kettles, showers, and trains. Daytime brings offices, shops, and industrial production. Evening often creates the largest demand peak. People cook, cool rooms, stream video, and charge devices. Operators forecast these patterns before they happen. When demand rises, more generation must join the system. When demand falls, some generators reduce their output. Frequency reveals whether supply and demand remain balanced. If demand exceeds supply, frequency begins to fall. If supply exceeds demand, frequency can rise. Large deviations can damage equipment and destabilize regions. That is why adjustments happen continuously. Reserve generators wait for sudden shortages. Energy storage can also respond within moments. Power can be rerouted around overloaded equipment. The grid behaves less like a pipe than a balancing act. Its stability depends on timing, coordination, and constant attention. Failures can begin with something surprisingly small. A tree branch may contact a power line. Lightning may strike exposed equipment. Heat can overload lines carrying too much current. A generator can suddenly trip offline. One failure can push extra load onto neighboring equipment. Those lines may then disconnect to protect themselves. The result can become a cascading blackout. A blackout is more than a dark skyline. Traffic lights fail and intersections become dangerous. Elevators stop, refrigeration warms, and payments disappear. Communications weaken as backup power runs down. Water systems may struggle when electric pumps stop. Hospitals switch to emergency generators and strict priorities. Protection systems are designed to stop failures spreading. Relays detect abnormal current, voltage, or frequency. Circuit breakers isolate the damaged section. Sensors report conditions across thousands of locations. Control centers combine that information into one picture. Operators restore power carefully, section by section. Restarting a dead grid can require special power sources. Recovery may take hours because everything must stay synchronized. The grid now faces challenges its designers never imagined. Electric vehicles add major new loads to neighborhoods. Data centers can consume power on the scale of cities. Hotter cities drive rapidly growing air conditioning demand. Meanwhile, more electricity comes from wind and solar. These sources are clean, but their output changes with weather. Solar production falls every evening as demand often rises. Wind generation can surge quickly, then fade. The grid, therefore, needs far greater flexibility. Large batteries store surplus electricity for later use. They release energy during peaks or sudden shortages. Pumped storage moves water uphill when power is abundant. Later, that water can generate electricity again. Smart meters reveal demand in far greater detail. Demand response can temporarily reduce non-essential consumption. Rooftop solar turns some consumers into producers. Microgrids can isolate and protect critical facilities. Modern power flow is becoming increasingly two-way. Software now coordinates millions of changing devices. The future grid will be more distributed and intelligent. Yet the basic purpose of the grid remains unchanged. It must deliver usable power exactly when people need it. Behind every skyline lies a deeper engineered system. Generators create energy from heat, motion, wind, and light. Transformers reshape that energy for each stage of travel. Towers and cables carry it across the landscape. Substations direct it through the network. Operators and software protect its balance every second. Millions of machines then turn electricity into modern life. Most people notice this system only when it disappears. But every glowing window is proof that it is working. Every small light represents an enormous chain of coordination. The grid is vast, delicate, and always awake. And that is how the world works. Every glass of water begins far beyond your kitchen. You turn a tap, and clean water appears immediately. It feels simple because the hard work remains invisible. Behind that tap lies an enormous engineered journey. Water travels through landscapes, machines, tanks, and buried pipes. It must be collected, cleaned, tested, stored, and pressurized. Every stage protects the people waiting at the other end. The system works continuously, even while the city sleeps. Pumps run, valves move, and sensors watch the flow. Millions of liters move without attracting attention. Most people notice this network only when it fails. This is the hidden machine behind every drop. The journey begins with the natural water cycle. Rain and snow replenish rivers, lakes, and underground aquifers. These sources become the raw supply for entire cities. Some cities depend mainly on rivers. Others rely on lakes or vast reservoirs. Many communities pump water from deep underground. Some coastal regions also remove salt from seawater. The source depends on geography, climate, and local demand. Whatever the source, quality changes from day to day. Storms can wash soil and debris into rivers. Drought can lower reservoirs and concentrate contaminants. Algae can grow when warm water receives too many nutrients. Groundwater may contain dissolved minerals from surrounding rock. Engineers must understand the source before designing treatment. The first protection often begins across the watershed itself. Healthy forests slow runoff and reduce erosion. Preventing pollution is easier than removing it afterward. But every city still needs a controlled intake point. Intakes bring raw water into the engineered network. Large screens stop branches, leaves, and floating debris. Fish protection systems can guide wildlife away from machinery. Pumps then lift water toward the treatment plant. Gravity sometimes performs part of this work for free. The incoming flow is measured before treatment begins. Operators watch temperature, turbidity, and chemical conditions. Turbidity describes how cloudy the water has become. Heavy rain can make turbidity rise within hours. The plant must adjust quickly when source conditions change. Raw water now enters the first major cleaning stage. Many plants begin by adding carefully selected chemicals. These chemicals help tiny particles lose their electrical stability. This process is called coagulation. Rapid mixers spread the coagulant throughout the water. Invisible particles begin forming small clusters. The water then moves into slower mixing chambers. Gentle movement encourages those clusters to grow. Large flock becomes heavy enough to settle. The water enters wide sedimentation tanks. Flow slows so gravity can separate solids from water. Mechanical scrapers move that sludge toward collection points. The removed solids require separate treatment and disposal. Clearer water leaves from the top of the basin, but it is not ready to drink yet. The next barrier is filtration. Water passes through layers of specially prepared material. Sand captures fine particles that escaped settling. Some filters also use activated carbon. Carbon can reduce tastes, odors, and organic compounds. Other plants use membranes with extremely small openings. Membranes can block particles, microorganisms, and dissolved material. Desalination relies heavily on reverse osmosis membranes. High pressure pushes water through while salts remain behind. Filters gradually become clogged during operation. Plants clean them using a process called backwashing. Dirty wash water is carried away for separate treatment. Filtration removes much, but one final biological barrier remains. Disinfection targets microorganisms too small to see. Chlorine is one of the most common disinfectants. It destroys many harmful organisms and protects distribution pipes. Some plants also use ultraviolet light. Ultraviolet energy damages microorganisms without adding chemicals. Ozone provides another powerful treatment option. Operators choose combinations suited to local water conditions. The disinfectant dose must be carefully controlled. Too little may leave biological risks behind. Too much can create taste problems or unwanted byproducts. Water chemistry is adjusted to protect pipes and public health. Stable water reduces corrosion inside the distribution network. Every chemical addition is measured and documented. The water now enters final quality testing. Laboratories check microbes, minerals, and chemical compounds. Online sensors provide continuous measurements. If results leave safe limits, alarms demand immediate action. Only then does treated water leave the plant. Clean water must now reach users at reliable pressure. Others first fill covered storage reservoirs. Storage balances treatment output against changing demand. Demand is usually lower during the night. Morning use can rise sharply within a short time. Stored water helps meet those sudden peaks. Elevated tanks use gravity to maintain pressure. The higher the water surface, the greater the available pressure. Pressure zones divide cities by elevation. Low areas require protection from excessive pressure. High areas may need additional pumping stations. Large transmission mains carry water across the city. Smaller distribution pipes branch into neighborhoods. Service lines connect individual buildings. Valves allow crews to isolate sections during repairs. Hydrants provide access for firefighting and maintenance. The network must preserve pressure without wasting energy. Every tap becomes the endpoint of this hydraulic system. Keeping water moving is only part of the challenge. A pressure loss can allow contamination to enter damaged pipes. That is why crews treat major main breaks as emergencies. Aging pipes can leak for years beneath busy streets. Some leaks reach the surface and become obvious. Others disappear underground without any visible warning. Utilities compare water produced with water actually billed. The difference can reveal hidden losses. Acoustic sensors listen for the sound of escaping water. Pressure sensors detect unusual changes across the network. Smart meters can expose abnormal household consumption. Robotic inspection tools can travel inside large pipes. Predictive software helps prioritize repairs before failure. Water towers and reservoirs are inspected continuously. Emergency generators keep critical pumps operating during blackouts. Redundant mains provide alternate routes when equipment fails. The strongest systems are designed around controlled resilience. The future water system must handle growing pressure. Cities are growing while many water sources become less reliable. Climate extremes bring both droughts and intense storms. Treatment plants must adapt to faster changes in raw water. Reuse can turn treated wastewater into a new supply. Desalination can support dry coastal regions. But both options require significant energy and infrastructure. Smart networks can reduce leaks and unnecessary pumping. Variable speed pumps match energy use to real demand. Local storage can strengthen resilience during emergencies. Protecting watersheds remains one of the cheapest solutions. The best technology still begins with a protected source. Every safe glass represents nature and engineering working together. From cloud to river, from plant to pipe, the journey never stops. Most of that journey remains buried, guarded, and unseen. Yet every neighborhood depends on it every hour. The system is vast, delicate, and constantly monitored. And that is how clean water reaches your tap. That is how the world works. Imagine that at midnight, every person responsible for running your city simply disappeared. No engineers, no delivery drivers, no control room operators, no repair crews. At first, almost nothing would seem different. The lights would still glow. Water would still leave the tap. Your phone would still connect. But beneath the streets, a countdown would already have begun. Because a city is not a place. It is a machine that must never stop. From above, a city looks like a collection of buildings. But look closer and it begins to resemble a living organism. Roads carry food and people like arteries. Power lines transmit energy like nerves. Water pipes move an essential fluid beneath the skin. Communication networks form a kind of shared brain. Millions of separate parts must cooperate every second just to create what we experience as an ordinary day. Begin with electricity. The energy lighting your room may have started hundreds of kilometers away, inside a dam, a wind turbine, a solar farm, or a power station. But generating electricity is only the beginning. It must travel through a vast network of transmission lines, transformers, substations, and cables. And unlike water or food, large amounts of electricity cannot simply sit on a shelf waiting to be used. At every moment, the electricity entering the grid must closely match the electricity being consumed. When millions of people wake up, start factories, charge vehicles, or switch on air conditioners, operators and automated systems must respond. Too little power can destabilize the network. Too much can also create problems. The entire grid is a continuous balancing act, performed so smoothly that most of us never realize it is happening. Before electricity reaches your home, its voltage is reduced in stages. Giant substations transform it for regional distribution. Smaller transformers prepare it for neighborhoods and buildings. Breakers and protective systems constantly watch for faults. When you press a light switch, you are completing the final step of a journey involving machines, computers, cables, and human decisions spread across an enormous distance. The result feels instant because the system is always ready. Now turn on a tap. The water may have begun as rain falling months or even years ago. It collected in a river, lake, reservoir, or underground aquifer. From there, pumps and gravity carried it toward a treatment plant. Before this water could safely enter your home, it had to pass through one of the most important and least visible industrial processes in modern civilization. Treatment begins by removing debris and suspended particles. Chemicals may help tiny impurities join together so they can settle out. Filters capture material too small to see easily. Disinfection reduces dangerous microorganisms. Sensors and laboratory workers check the water throughout the process. Only after meeting strict safety requirements does it enter the distribution network. A hidden maze of pipes running beneath roads, buildings, and sidewalks. Water must arrive with enough pressure to climb buildings and flow from taps, even during periods of high demand. Pumps provide much of that force, elevated tanks and reservoirs. Use gravity while also storing water for peak periods and emergencies. Pressure zones help serve neighborhoods at different heights. Every glass of water depends on carefully managed pressure. Too little, and upper floors go dry. Too much and aging pipes can break. The system does not end when water disappears down the drain. Wastewater flows through another underground network toward treatment facilities. Screens remove large objects. Tanks separate solids. In many plants, microorganisms consume dissolved waste while oxygen is pumped into the water. The treated water can then be safely released or reused. Without this system, disease and pollution would spread rapidly. Modern sanitation is one of humanity's greatest invisible achievements. Then there is everything the city throws away. Every day, homes, restaurants, offices, hospitals, and factories produce a mountain of waste. Collection vehicles move through carefully planned routes, often while most residents are asleep. Recyclable material may be sorted by machines and workers. Organic waste may become compost or energy. The rest must be contained and monitored. Waste appears to vanish only because an enormous system carries it somewhere else. A city also needs to eat. Most urban residents produce almost none of their own food, yet stores remain filled with products from farms, factories, and oceans around the world. Behind every shelf is a chain of growers, processors, warehouses, ships, trains, trucks, and software. Deliveries must arrive in the correct order, at the correct temperature, before the food spoils, and before millions of customers decide what to buy. Perishable food depends on the cold chain, an uninterrupted series of refrigerated spaces. A fish may remain cold from the moment it leaves the water until it reaches a restaurant. Vaccines, medicines, dairy products, meat, and fresh produce rely on similar control. A delay, failed refrigerator, or incorrect temperature can ruin an entire shipment. The abundance inside a supermarket is therefore not permanent. It is a carefully maintained flow. People must move as well. Roads, railways, buses, sidewalks, bicycle routes, bridges, and tunnels form overlapping transport networks. Each has limited capacity. When too many travelers choose the same route at the same time, congestion appears. Traffic engineers study these flows, much like water engineers study pipes. They adjust signals, redesign intersections, schedule trains, and respond to accidents, all to keep the human current moving. Much of transportation is really a problem of timing. Signals can be coordinated, so vehicles meet a sequence of green lights. Trains must maintain safe distances, while arriving frequently enough to carry crowds. Buses need to connect with other routes. Deliveries avoid the busiest hours. A difference of just a few seconds, repeated across thousands of intersections and journeys, can determine whether a city flows smoothly or becomes trapped in its own movement. Another kind of traffic moves beneath the streets. Data. Messages, videos, bank transfers, navigation requests, and business records travel mainly through physical cables. Fiber optic lines carry information as pulses of light. Data centers store and process enormous volumes of it. Undersea cables connect continents. What we call the cloud is not floating above us. It is a worldwide collection of buildings, machines, cables, cooling systems, and electrical connections. When you use a mobile phone, it communicates by radio with a nearby antenna. The network then decides how to route your call or data, often through cables for most of the journey. As you move, the connection is handed from one cell to another. Thousands of devices may compete for access in a small area. The experience feels wireless, but behind that final radio link stands an intensely physical infrastructure. Money has its own infrastructure. When you tap a card, the payment does not simply jump from your account to a shop. A message travels through payment networks and financial institutions. Systems check the account, look for signs of fraud, approve or reject the transaction, and record what happened. Settlement between institutions may occur later. In seconds, multiple organizations coordinate to create the simple message. Payment approved. Some services cannot tolerate even a brief interruption. Hospitals need reliable power, clean water, medical gases, communications, sterile supplies, and trained staff. Emergency dispatchers must identify where help is needed and which team can respond fastest. Backup generators wait for power failures. Fire stations track equipment and water access. These systems are designed with layers of protection because, during an emergency, ordinary infrastructure becomes a matter of life and death. Even a highly electric city still depends on fuel. Ships, aircraft, construction equipment, emergency vehicles, backup generators, and many delivery fleets require a steady energy supply. Fuel moves through ports, refineries, pipelines, storage terminals, and trucks before reaching the machines that use it. If one link fails, the effects travel outward. Delivery slow. Repairs are delayed. Backup systems lose their backup. Energy connects nearly every other urban network. Every part of the city is slowly wearing out. Metal corrodes, concrete cracks, filters clog, batteries weaken, roads deform under traffic and weather. Maintenance teams search for small failures before they become large ones. Increasingly, sensors reveal changes in temperature, pressure, vibration, or electrical current. But technology does not eliminate maintenance. It helps people decide what to inspect first in a machine far too large to examine all at once. The city never truly operates by itself. While most residents sleep, operators monitor power. Engineers inspect water systems. Bakers prepare the morning's bread. Mechanics repair trains. Cleaners restore public spaces. Drivers bring food into markets. Security teams watch critical facilities. Their work is often invisible precisely because it succeeds. We notice infrastructure when it fails, but rarely notice the people who prevent that failure every ordinary night. Cities must also prepare for events they cannot control. A storm increases electricity faults, blocks roads, floods tunnels, and overwhelms drainage systems at the same time. Forecasts give operators time to position repair crews, lower reservoir levels, protect equipment, and warn the public. Planning does not prevent the storm. It changes what happens next. Resilience is the ability to absorb a shock without allowing every connected system to collapse. Because urban systems are connected, failure can spread like falling dominoes. A power outage may stop water pumps and traffic signals. Congestion can delay repair crews and fuel deliveries. Communication towers may continue on batteries, but only temporarily. Shops may function, but no functioning payment systems. Each service depends on others, and those dependencies are not always obvious until something breaks. This is called a cascading failure. A blackout may begin with a damaged line, failed machine, extreme weather event, or unexpected imbalance. Protective devices disconnect the affected equipment to prevent greater damage. But the electricity that once used that route must go somewhere else. Neighboring lines can become overloaded and disconnect as well. Operators must isolate the problem, stabilize the remaining network, and understand what happened before they can safely restore power. Recovery happens in stages. Critical services such as hospitals, communications, and water infrastructure receive priority. Power stations and transmission paths must be restarted in a controlled sequence. Adding too much demand too quickly can destabilize the grid again. Similar priorities guide recovery from floods, earthquakes, and cyber attacks. Restoring a city is not like flipping one giant switch. It is more like rebuilding a living network, connection by connection. The secret holding all of this together is coordination. Power companies speak with emergency services. Water operators monitor electricity risks. Transport agencies share information about closed roads. Hospitals track available capacity. Businesses adjust deliveries. No single person controls the entire city, yet thousands of decisions combine into organized behavior. The city's true operating system is not one computer. It is communication between people, institutions, rules, and machines. There is always a tension between efficiency and resilience. One large pipeline may be cheaper than several smaller ones. A warehouse with minimal inventory costs less to operate. A tightly scheduled network wastes little capacity, but efficiency can create fragility. Resilient systems include spare capacity, alternative routes, backup power, stored supplies, and trained people. These protections may look unnecessary. Right up to the moment they become essential. You are not merely a passenger inside this machine. Your choices affect its behavior. Electricity use changes demand on the grid. Travel choices shape congestion. What you throw away influences waste systems. During emergencies, accurate information and responsible behavior can reduce pressure on essential services. Even allowing an ambulance to pass is a tiny act of system coordination. A city works because millions of people participate, usually without thinking about it. The next time you drink a glass of water, cross an intersection, buy fresh food, or send a message across the world, pause for a moment. Behind that simple action is a chain of systems stretching far beyond what you can see. Pipes, cables, roads, machines, software, and people are working together to make the ordinary possible. Civilization is not only what we build, it is what we continuously maintain. A city may look permanent, but every ordinary morning is an achievement repeated from scratch. Energy must flow. Water must move, food must arrive, waste must leave, information must connect, and people must keep every part working. This hidden machine is complex, imperfect, and surprisingly fragile. But it is also one of humanity's greatest creations. And once you learn to see it, the world around you will never look ordinary again. This is how the world works.